So looking at the formation of a racemic mixture in the radical reaction, uh, whether our carbon is sp2 hybridized and planar or sp3 hybridized and undergoing interconversion of a rapid shallow pyramid, in either case, we have a situation where we are essentially periplanar or near planar, so that attack from either side is equally probable. So that is our explanation for the stereochemistry of the radical reaction. If we look at this example of butane, the secondary carbon position is the favored position for reaction because the secondary carbon radical is the most stable. Therefore, this bond is the easiest to break, and we will form a racemate. So these two will be in equal proportion. Earlier, we said that the substitution at the secondary position would be about 60%, while substitution at the primary position would be about 40%. So we're looking at 40, 30, 30 in terms of our total product distribution. As I was saying, the free radical stabilization trends follow the same trends that we learned when we were looking at the carbocation. Our secondary position is a much weaker bond, so this is where the reaction will take place. If we look at the allylic position, the same sort of trends are observed. We will selectively undergo hydrogen abstraction at the allylic carbon, and the bond densities, bear that out. So in this example, you recognize there are two allylic positions, so we will still get a mix of products. Because there are no other substituents, that spatial distribution has no net effect. But if we were working with a substituted molecule, we would be looking at different products. One of the things that we want to consider with the bromination at the allylic position is that while this is the favored location for our radical reaction, we will still have the possibility of adding bromine across the double bond. So this will be a competing reaction. The way to avoid this is to work with a low concentration of bromine, which will favor the radical mechanism. And to do that, we can use the reagent N-bromosuccinimide. And bromosuccinimide will give us a low level of bromine to give us bromine in the reaction, but at a very low concentration. We're just generating it in situ. So, in this case, we have the abstraction form HBr. Product will be HBr. We will also produce succinimide in this reaction. The HBr that's produced reacts with NBS to form a very low level of bromine, and this will undergo homolytic cleavage to give us our bromine radicals without having a sufficient concentration to lead to the addition product. And in this way, we can have a selective bromination at the allylic position. Looking at a asymmetric alkene, we're going to see a mixture of isomeric products. In this case, the allylic position is also a tertiary carbon, so this is a favored location. In our resonance stabilized structure, we also have direction of the bromine at the allylic position. So this radical can be delocalized on the two carbon atoms. So halogenation will take place at either site.